Welcome back to AP Stats. Again, I'm not affiliated with the College Board. I teach at a local high school where they call me Dr. Kling. And this is the 11th talk, and it'll be the last one on the subject of conditional probability. And I call it the doctor's mistake. The doctor's mistake. And I put the apostrophe where I meant to because many doctors make this mistake. I've had a doctor make this mistake with me, not in this particular diagnosis, but in an analogous situation. Okay, so what is this mistake? I got this from a book, and the book is called Super Crunchers by a fellow named Ian Ayres. There we go, Ian Ayres. And so what he reports is that when doctors are asked a question, so several studies have asked physicians over the years the following type of question. 1% of women at age 40 who participate in routine screening have breast cancer. 80% of women with breast cancer will get positive mammography. 10% of women without breast cancer will also get positive mammographies. What is the probability that someone who has a positive mammography actually has breast cancer? So I've reproduced the numbers down here. So event A is you have cancer. Event B is you test positive. And the question asks, if you test positive, what is the probability that you have cancer? What is the probability of A given B? This is what the doctors are asked to solve for. Or guess if they don't know how to solve for it. And so the probability of A, the probability that they have cancer, that just a random woman has cancer at that age, is 1% in this problem. The probability that they test positive if they have cancer is 0.8. The probability that they test positive if they don't have cancer is 0.10. So that's the information we're given, and we can use it to solve the problem using our box and triangle methods. So let's do that quickly. I think I can do it quickly. Okay, so we have our friends A and B and BC and AC. And we know that A is 0.01, which means that AC is 0.99. And we have B is we don't have B, so we're going to have to solve for B. We're going to have to use triangles. So we use the triangle involving B and A here, and the triangle involving B and AC here. So we'll say that the probability of B and A is equal to the probability of B given A times the probability of A, which is equal to 0.8 times 0.01 is equal to 0.008. So we put a 0.008 there. And then for B and AC, we'll use probability of B given AC times probability of AC, and that will give us 0.10 is the first thing, times AC, which is 0.99, which looks like 0.099. So we have a 0.099 there, which means here if we add this up, I think we get something like 0.177. 71, is that right? Maybe it's 187? 71, no. It's 0.107. Is that right? Yeah, 0.1. Sorry about that. 99,8107. Okay, so we have that. And now what we want to find is probability of A given B. Now we have B, so that's equal to probability of A and B over probability of B, and so that's 0.008 over 0.107. Hang on, I'm going to use a calculator for that one. Hold on a second. Okay, I got that one now. It's equal to 0.0748, something like that. Alright, so there's our answer. It's about 0.075. Well, what did the doctors typically get when they did this problem? And the answer to that one is this. Okay, in study after study, most physicians tend to estimate that the probability of cancer is about 75%. Actually, this answer is about 10 times too high. So the doctors think that this is 0.75 when it's 0.075. And I've had this happen to me with a different thing. Obviously, it wasn't a breast cancer diagnosis. It was something that led to a very painful and terrifying test, which was totally unnecessary. And it's really because doctors don't intuitively understand Bayes' theorem, and then they don't use Bayes' theorem in practice. So hopefully if you grow up and become doctors, you won't be making this very common doctor's mistake. And I think I'll leave it at that, and next time we'll move on to a new topic.